I want to measure my car's miles per gallon. So I make one measurement. I could do this if I want to by like filling up my car's gas tank, resetting the odometer, driving around for a while, coming back to the gas station, fill up my car's gas tank again, look and see how many gallons of gas it took to refill the car's tank, look at my odometer reading, and then I could divide. Gallons of gas divided by miles driven, or opposite. I'd actually divide miles driven divided by gallons of gas. And so let's say I do that, and I make one measurement, and it's like 33.2 miles per gallon. But this is not going to be a perfectly accurate reflection of the distribution mean. There's a lot of things that factor into this, right? Like depending on what gas pump I go to, I might get more or less gas in my tank. And then what about driving conditions, right? Like how much time do I spend idling my car in between trips to the gas station? A lot of different stuff. Weather. So instead of just taking one measurement, I might take several measurements and then calculate the sample mean. So here's my sample of 7 different measurements. And if I were to then go ahead and repeat this process 100 times so that I have like 700 different measurements, and I'm constantly taking groups of 7 and calculating the mean, I would find out that I don't get the sample mean every time. The sample mean is a randomly distributed, it's a random variable. It also has a probability distribution. And we mentioned this before, that if the sample size is greater than or equal to 30, then we say the sample mean is normally distributed. This is something we said on Friday. If the sample size is less than 30, then it's not normally distributed unless it happens to be that the underlying distribution is normally distributed. Then in that case, it is still normally distributed. Our best approximation of this standard deviation of the sample mean is called the standard of error of the sample mean, and that's the formula. Kind of been talking about this a lot. And one last thing I'll say is, if I ask you on a test, what's the effect of the sample size? And a larger sample size makes the standard deviation of the sample mean smaller, right? Because it's in the denominator. That's all you have to say. So a 95% confidence interval is an interval along the real number line that contains the most probable 95% of outcomes from a random process generating a statistic like the sample mean. We did this before with the sample fraction. Now we're going to do this with the sample mean. This is new. We've not talked about prediction intervals yet. A 95% prediction interval is an interval along the real number line that contains the most probable 95% of next outcomes from a random process. The level of significance, you know what that is? If I have a 95% confidence interval, the level of significance is 0.05. Critical values. When we were talking about confidence intervals about a population fraction, my critical values were little lowercase z's. And we used the standard normal CDF to look up the, no, we didn't use the CDF, we used the quantile function. We used the standard normal quantile function to look up the, I don't know what the right word for it is anymore. Forgot my vocabulary. But what's my point? We have little lowercase t's now instead of z's. Whenever we're talking about the sample mean and the population mean, we're going to use these little t critical values. And that means whenever I take the quantile function of 1 minus alpha over 2, this is not the standard normal distribution quantile function, this is the t distribution quantile function. You actually do have a paper of t distribution quantile function that I passed out at the start of class. And you still have a different distribution for every degree of freedom. So you'll notice that the rows on this table are degrees of freedom. You get a bunch of different t distributions for different degrees of freedom. Because we really only care about the quantile function for really specific values. Those are the columns on top. So if you're like, what is my alpha over 2? That's the columns of that table. The degrees of freedom is going to be the sample size minus 1. So when it says calculate the following critical value, the way I would do that for t 0.025, wonder where I set my little pin. It's in my pocket. Here we go. So I'm going to look at the quantile function table. And I'll look up 1 minus 0.025. Except that there's only so much room on that page. And so I didn't actually put down the quantile function of what is 1 minus? That would be 0.975. Yeah, that's right. This is not on the page for the quantile function. So instead, what I could do is I'm just going to take the absolute value of what I get if I plug in 0.025. Why does this work? Because the t distribution, like the normal distribution, is symmetric. You could also do this with the standard normal distribution if you want to. For the standard normal distribution, we actually have all of the numbers on the quantile function page, so we don't really have to think about it. The trouble with the t distribution is that you've got all these different degrees of freedom that we want to represent, so it really limits the amount of page space I have to include a bunch of extra numbers. And because of that, we can just rely on little tricks like this. Let's look up the quantile function of the t distribution at 0.025. Oh, and I also need to know my sample size. For a t distribution, we need to know my sample size. And let's just say n is equal to 25. So then my degrees of freedom are going to be the sample size minus 1, which is going to be 24. So now let's look at the t distribution with 24 degrees of freedom at 0.025. Here's my t distribution quantile function. I need 24 degrees of freedom, so I'm talking about this row, at 0.025 is this column. So my number is negative 2.0639. Negative 2.0639. Okay.
It's negative 3.09. Oh, wait, never mind.
Oh yeah, you were looking at the 0.0025. Yeah. Now, I take the absolute value. That just means make that number positive. That is the critical value. And again, the trick here where I just plug in 0.025 and then make it positive is because these are symmetric about 0. Let's look at my t-distribution with sample size 25 here. If I want the area to the left of negative 2.0639, I'm talking about this little orange area. But since this is symmetric about 0, if I took the area to the right of positive 2.0639, that's going to be the same shape, the same size, the same area. I'll show you. You just change this to right, change this to positive, boop. Still the same area, still 0.025. You make it negative, you make it left, still 0.025. That's why that little trick works.
So do we always take the absolute value? Or like, how do we know when to do that?
It's a good question. Yeah, I think the answer is yes. If you were making a confidence interval and you're looking up a critical value, you should always expect to have a positive number critical value. And if it's negative, just make it positive.
Do we have to do the 1 minus?
No?
So we just look up the number? We don't have to do the 1 minus?
Yeah, that's the idea. Is that because of this symmetry, the quantile function of 1 minus 0.025 is the same thing as the absolute value of the quantile function of 0.025. That happens because of symmetry. And the t-distribution is symmetric, so that will always happen. So that's what you do. Yeah?
So you just, like, for the sample size, you just said it was 25. Like, you just made...
I will tell you the sample size, right? Like, whenever I give you this question on a test, on homework, I'll make sure that I will, I'll make sure that I do that. So, like, I'm almost done writing this homework, but I actually thought about that while I was writing the homework. I was like, I'm going to actually tell you a sample size when I ask you to calculate a critical value. Good question.
Will you make it clear on the test which one you're wanting, like for the mean and then the population fraction and all that?
Yeah.
Like okay. Will there ever be a question where to do both in the same one?
No. Okay, so first we're going to talk about how to calculate a prediction interval. If I want to calculate a prediction interval, it looks really similar to the process of constructing a confidence interval that you saw a couple weeks ago. We're going to calculate the level of significance, we're going to calculate the critical value, we're going to calculate the margin of error, and then we're going to write the confidence interval as the sample mean minus the margin of error up to the sample mean plus the margin of error. So if I wanted a 95% prediction interval, the level of significance is going to be 0.05. That should look kind of familiar to you, right? 95%, you've got 5% missing, 5% as a decimal is 0.05. Then we calculate a critical value. And for that critical value, I would have to do what we just did, look up in the t-distribution quantile function what would be half of alpha, right? Not just 0.05, but that divided by 2, which is 0.025. And then take the absolute value, so I get 2.2622. The margin of error is going to be this critical value times the sample standard deviation.
Is the sample's deviation the normal, like, standard deviation?
Mm-hmm. So the sample standard deviation is calculated by taking the square root of the sample variance, and the sample variance is like the sum of all of the measurements minus the mean squared. So you have to calculate the sample mean first, and then you take each measurement minus the mean. You take that difference and you square it, and then you add all of those up, and then you divide by n minus 1, and then you take the square root. It's a really long process to get the sample standard deviation.
Didn't you give us this, what it is on the last test? Or do we have to work on it?
I'll probably, I don't know. I don't want to rule out the possibility that I could, this was the problem on our very first test, remember? I accidentally had you guys calculate a sample standard deviation for like a sample of like size 20. And so I would only make you calculate a sample standard deviation for a small sample of size like 4, if that were to appear on the test. The other option is maybe I'll just tell you what that number is. And the other option is maybe I give you a really small sample size, like a sample size of 3 or 4. Because you're right, that's a long calculation. And then the last step is I've already found my margin of error. I just find my prediction interval by taking the sample mean minus the margin of error, the sample mean plus the margin of error. So we'll do one of those examples later. Next, I want to tell you about the confidence interval. A confidence interval for a mean looks exactly the same. That's supposed to start from number 1, 2, 3, 4. But step 1 is calculate the level of significance. Step 2 is you look up that critical value in the t-table. Step number 3, you calculate the margin of error. And step number 4, the margin of error is the sort of radius of the confidence interval. The only difference here is this. This is not the sample standard deviation, is it? This is the standard error of the mean. Which is the sample standard deviation divided by the square root of n. That's the only difference between calculating a prediction interval and calculating a confidence interval, is that one change. Otherwise, exactly the same. When I do this, when I make a confidence interval that has the standard error of the mean and a prediction interval that has the sample standard deviation, we're going to find that the prediction interval is always going to be a lot wider than the confidence interval. The prediction interval is saying, I'm 95% certain that the next outcome of my random process is going to be inside this interval. The confidence interval is saying, by following this procedure, 95% of randomly selected samples will give me a confidence interval containing the population mean. So confidence intervals end up being smaller. than prediction intervals. All right, so let's do an example. I want to measure the relative humidity in the air, so I use a sling psychrometer. I take 5 measurements at the same time in the same place. Since the sling psychrometer isn't a terribly accurate measuring device, construct a 90% confidence interval for the true value of the relative humidity. So this is a lot of work, but this is what we're going to do. Step number 1, since I don't already know the sample mean, is we got to find the sample mean. We've got to add up all of these numbers and then divide by 5. And then step number 2, I want to find the sample standard deviation, which is going to be the square root of 43 minus 39 squared plus 35 minus 39 squared plus 37 minus 39 squared plus 42 minus 39 squared plus 38 minus 39 squared divided by 4, right, divided by n minus 1. And so I've got 4 squared is 16, 4 squared is 16, 2 squared is 4, 3 squared is 9, 1 squared is 1, divided by 4, which is 32, 36, 45, 46, 46 divided by 4, square root of 11.5, .391. Okay, so that's how you do a sample standard deviation. Step number 3, I'm looking for a confidence interval, and so I'm going to need to know what is the standard error of the mean eventually. And so the standard error of the mean is going to be the sample standard deviation divided by the square root of n, my sample size. So that'll be 3.391 divided by the square root of 5. It's going to be 1.517. All right, then we think about my level of confidence is 90%. 90% confidence means alpha is yeah. Alpha will be 0.1 or 0.10 because 90% is missing 10%. 10% has a decimal of 0.1. And then my critical value, T alpha over 2, is going to be the quantile function, and then I'll take the absolute value and just plug in 0.1, right? We look this up in the table, and how many degrees of freedom do I have? That's right. So 4 degrees of freedom, 0.1. My number is negative 1.5332. But I'm taking the absolute value, so I should just call it 1.5332. My margin of error is going to be my critical value times my standard error of the mean. So in other words, that's going to be 1.5332 times 1.517, and that gives me 2.326 as my margin of error. And then finally, I'm ready to write down my confidence interval. My confidence interval is going to be this sample mean plus or minus the margin of error. So like, the sample mean was 39. Yeah, 39. So we'll go from 36.67 up to 41.33. That is my confidence interval. In the context of my problem here, it's like, okay, I took 5 measurements of the relative humidity. What it means is that I've got like 90% confidence that the actual value of the relative humidity outside is between 36.7 and 41.3% relative humidity. And if you want to be really, really particular about it, what you say is, by following this exact calculation procedure, I know that 90% of the random samples I take from this probability distribution are going to generate this confidence interval that will include the true value, or the mean of the distribution. But that's the idea. All right, so we'll pick up here next time we meet. Yep.
When we find critical value, why do we put alpha divided by 2?
Why did we do what?
Critical value, why did we put alpha and not alpha?
Oh, you're right. I made a mistake. Thank you. Great question. It should be 0.05. Because this should be alpha divided by 2, not just alpha. I just plugged in alpha. So, easy mistake to make, I guess. Got to watch out for that.
So it changes our answer?
Yeah, we'll definitely change your answer because you'll get a different critical value here. That will be different. And so all of this is going to be different.
Oh, I'm bored. Can I ask you something about the...
Can you actually?
Yeah.
So I just want to make sure I did this right. So
You probably want to know now, with Desmos, how would I go about calculating a critical value from the t-distribution? Like, for example, the critical value is 0.025, where the sample size is 8. Here's how you do it. You say, if my sample size is 8, then my degrees of freedom is 7. So I've got 7 degrees of freedom, and I've got a critical value t subscript 0.025. And this, remember, is going to be my t-distribution quantile function evaluated at 1 minus 0.025. So in other words, the quantile function at 0.975. And let's do this in Desmos. 0.975.
So do we not
7 degrees
the
of freedom.
absolute value? I know
Oh, yeah, you don't have to now that we have Desmos.
Okay.
We were doing that because we were dealing with the tables. But in Desmos, what you do is you say, I want a t-distribution, and then I have 7 degrees of freedom. So the degrees of freedom goes inside the parentheses. I want the quantile function, so I'm going to choose left bounds to get the quantile. And then where it asks me, the blank right here, this is where I'm going to put in 0.975. So what the quantile function is telling me is, if I want the blue shaded region to include 0.975 of the area under the curve, then this point right here, where the blue shaded region cuts off, has to have a value of 2.365. No.
Oh, that's the free.
7 is the degrees of freedom, and the degrees of freedom is always 1 less than the sample size.
So then the 2.365 would be the t value?
Yeah, you're right. So where it says 2.365, that's my answer. That's the critical value.
Where do you find the degrees of freedom?
The degrees of freedom is 1 less than the sample size.
Okay.
And so if I tell you n equals 8, the sample size is 8. And so the degrees of freedom will be 7.
Was that on?
I think I revised my notes to include this. But it's on all the homework questions. Okay, so did we talk about constructing a prediction interval? I think we did. We talked about the prediction interval. We talked about the confidence interval. Okay. Yeah. So let's do this. I want to measure the relative humidity in the air. So we're using a sling psychrometer. I take 5 measurements. Here are my measurements. What we do first, I think we maybe even did this problem, didn't we?
Yes, we did.
Okay. Did we do the entire problem, or did we have to stop?
Margin of error.
Okay, let's do it again. Really quick. 43 plus 35 plus 37 plus 42 plus 38 divided by 5 is 39. And what was my standard deviation?
At 3.39.
Okay, and then I need my standard error of the mean, and that would be the standard deviation divided by square root of n. It was 1.517. Cool. Now, shortcut time, because we're going to use our phones, right? Everybody's on board. We're going to use Desmos. Here's a little Desmos shortcut for you. I want a 90% confidence interval. My sample mean is 39, and the standard error of the mean is 1.517. So let's go to Desmos here. And I'm going to create a normal distribution. And the mean of this normal distribution is going to be 39. And the standard error was 1.3 something. 1.517. So that's what it looks like. That's my probability distribution. Okay, how do I now construct a confidence interval? A 90% confidence interval. I'm going to click cumulative probability. And then I'm going to choose inner, and then I'm going to choose bounds for the confidence interval. And then when I choose bounds, it's going to ask me, what do I want the probability to be equal to for a 90% confidence interval? What do I type in? 0.9. I want 90% confidence, so I want the probability to be 90% of the probability.
What do you put in the bounds?
Lower bound, upper bound.
We just, does it already just put those in for you?
Yep.
You don't have to find them. So on the test, do we need to?
No, it calculates those. So right here, this is what you control. This is my percent confidence, right? If I want my confidence to be 90%, it's going to tell me these lower bound, upper bound. If I want my confidence to be higher, do you see why my bounds would have to be wider for a larger degree of confidence? And then if I want my confidence to be small, well then the bounds get really close together. But my point is they calculate the lower bound, upper bound for you.
So then you won't need the margin of errors.
I could still ask you to find the margin of error.
Is that not the bounds?
The margin of error is half the width of the confidence interval. So when we were talking about capital E margin of error, this is half of the width of the confidence interval. So the sample mean goes in the middle. The lower bound is 1 minus the margin, or sorry, is the sample mean minus the margin of error. The upper bound is the sample mean plus the margin of error. In fact, this is a nice picture because I've got it shown. Sample mean in the middle, and the margin of error is half the width of the interval. But even then, you can imagine a shortcut for calculating the margin of error. Go into Desmos, create the confidence interval, subtract, do the upper bound minus the lower bound, and then divide by 2. Like, I could get my calculator out, and I could type in 41.5 minus 36.5. So the width of my interval is 5, then divide by 2, and I get a margin of error of 2.5. Does that make sense?
The margin of error was 2.326.
Yeah, it's probably because I rounded off too much. Oh no. Okay, I made a big mistake. Do you see the mistake? Yeah. I ought to be using a t distribution, not a normal distribution.
Wait, why?
Oh my goodness.
Wait.
Okay.
Wait, why?
When we were doing the sample fraction, right? The sample fraction, population fraction stuff, when we were doing the confidence interval, the hypothesis test, we were always using the normal distribution. But whenever we do the sample mean, population mean, any of this kind of stuff, we have to use a t distribution. So that's important. The t distribution, because we don't actually know what the standard deviation is. We're relying on our estimate, our sample standard deviation, to sub in for the real standard deviation. That introduces more uncertainty. That means we can't use the normal distribution. We have to use the t distribution. It has a little bit heavier tails to account for that extra uncertainty. And so now let's use the t distribution, and I bet we'll get the right answer, right? We just have to say, what was my sample size? 5. If my sample size is 5, 1, 2, 3, 4, 5. Then what is my degrees of freedom? 4. So I need to use a t-distribution with 4 degrees of freedom.
Wait, we're keeping 39.
What is 4, 39,
Okay, so we got a lower bound of 35.77 and 42.23. I wonder if that's the same thing we got on Tuesday.
It's not.
It's not? That's interesting.
Isn't it the sample mean plus or minus the error,
Uh-huh.
margin of error?
Yeah. So I wonder why we got a different answer. We'll find out. 35.77, 42.23.
I hit right and it gave me the right answer.
You did what?
Like I hit right and then it gave me 36.67, which is what we got on Tuesday.
42.23. Oh, well, you remember,
Wasn't this the question that
don't you remember? We made a big mistake on Tuesday. I used alpha, not alpha divided by 2 when I calculated the critical value. So we actually got the wrong answer on Tuesday. Yeah. So if on Tuesday we actually used alpha divided by 2 and not just alpha, then we would have gotten the right answer. This is the right answer. Yeah. So
Wait, so is the margin of error still 2.5 or no?
nope. It'll be the 42 minus the 35. 42.35 minus 35.77 divided by 2.
Is there a way to redo that?
So what's the margin?
Because now I'm confused.
That's the margin of error.
And then what's the T alpha divided by 2?
So alpha is 0.1. Alpha divided by 2 is 0.05. T alpha over 2 would be T 0.05, which would be the quantile function evaluated at 1 minus 0.05, which would be the quantile function evaluated at 0.95. And the quantile function evaluated at 0.95 would be this. I would take the t-distribution with 4 degrees of freedom. I would click left, and then I would say I want the bounds. I would put in 0.95. So it's 2.132.
Do we not have a quantile one?
How do we find the required sample size? Choose your desired level of confidence. A lot of people like to make 95% confidence intervals, so your level of confidence might be 95%. Calculate your level of significance. Of course, that's like 100% minus your level of confidence, and then represent that as a decimal. Calculate the critical value. The critical value is something we can get from my level of confidence. Your level of significance. You take your level of significance, you divide it by 2. You put that in the quantile function of your t-distribution with, oh, sorry. I don't know why this says t-distribution. Because we don't know what the sample size is. I think I must have copied and pasted this somewhere, but doesn't make any sense. If we don't know what the sample size is, then we are going to use the standard normal distribution. So I should really use a z there for the standard normal distribution critical value. Then we can calculate the required sample size like this. You take your critical value that you get from the standard normal distribution, you multiply by the sample standard deviation you calculate, you divide by the desired margin of error, because you get to choose the margin of error you want when we're finding a sample size, and then you square that. Round up, and that's your sample size. So you're like, well, if I don't have a sample, how do I calculate this sample standard deviation? And the answer is you use a pilot study. So if you think your actual study, your actual experiment is going to require a massive sample size with like hundreds of subjects, well then what you should do is first do a little experiment with like 5 or 10 or 15 subjects, calculate their sample standard deviation, so that you can use that sample standard deviation from your pilot study in this formula, and this formula will tell you the actual number of subjects that you need for your actual experiment that you're going to carry out. You could just play it safe and recruit 1,000 subjects, but that would just cost more money, it would take more time, it would require more resources, and so using a pilot study is trying to find a way to preserve or be a good steward of the resources you're given, and only get the sample size that you need. Of course, a bigger sample size is always better, but we just don't always have the resources for it. Maybe your grant money doesn't provide enough for you to have a massive sample. And there's no way to do this without a pilot study. You know, when we were talking about doing hypothesis testing and confidence intervals about a fraction, like a sample fraction, population fraction, there was an alternate formula that you could use if you didn't want to do a pilot study, but in this case, there is no alternate formula. You need to have some kind of estimate for what your standard deviation is. You can't get around that this time when we're talking about constructing a confidence interval about a population mean. So we'll do one quick example and then we'll move on to the next thing. I want to know the average age of an MNU student in the professional and graduate programs, so I conduct a survey. I want to know the average age with 95% confidence. Oops. 95% confidence tells me that my level of significance alpha is 0.05 to within plus or minus 2 years. Plus or minus 2 years, that tells me my margin of error is 2. Suppose pilot data reveals S is equal to 6. So I've gone around and asked just a few students. This isn't the real study, but I just went ahead and asked a few people what their age is in the professional graduate programs, and I found that their standard deviation of my results was 6. How many students do I need to survey? So we say N is equal to the critical value times the sample standard deviation divided by the margin of error that I want, squared. I just need to know what that critical value is, and I'll be ready to go. So my critical value is going to be the quantile function evaluated at 1 minus alpha over 2, which is going to be my standard normal distribution quantile function valued at 0.9, not 0.0, 0.975. This time I actually remembered to divide alpha by 2.
do we have
Yep.
a sheet of paper?
Quantile function is in Desmos, yeah. So I would, always recommend that you practice a little bit with that Desmos app before test day. And of course, this is what it looks like. You're going to click the button that says Func in the app. Here it says Functions. And then you scroll down to probability distributions. You find normal distribution. Then to get the quantile function, I'm going to hit left bounds. And in the blank, where, too far. In this blank where it lets me type in the blank, I'm going to type in 0.975. And then where it gives me a value for the upper bound, that's what I get from the quantile function. That's the output of the quantile function. It's telling me 1.96.
What would be the CDF? Is there a CDF?
The CDF is left area. The quantile function is left bounds.
When would you use a CDF?
We use the CDF whenever we are calculating p-values in a hypothesis test. We use the quantile function when we are calculating the critical values for a confidence interval.
And that's the only time you use the quantile?
Right.
Okay. This is only for confidence intervals?
Yeah, that's a good question. Let me write this on a piece of paper somewhere. Because, in this next test number 3, we've got 8 sections. And in section 3.2, we were doing confidence intervals about 1 fraction. In section 3.6, we were doing confidence intervals about 1 mean. And these were both cases where we were using the quantile function. In 3.3, we were doing hypothesis testing about statements about 1 fraction. In 3.4, we were doing hypothesis testing about statements about 2 fractions. You're making a claim about 2 population fractions. In section 3.7, we were doing hypothesis testing about 1 mean. Well, actually, we haven't gotten to that yet, but we will by the end of class today. And then the last thing we're going to talk about in our inference unit is hypothesis tests about claims regarding 2 population means. And so for all of these, you're going to end up having to use the CDF, or cumulative distribution function, which is the left area part, to find p-values. On Desmos, use left bounds for the quantile function and use left area for the CDF. Question?
But if we're counting the critical value but for the t-distribution, what do we put in? Like, what is that? Left area or left bounds?
If you want the quantile function for the t-distribution,
Yeah.
yep.
So we'll just put left bounds.
Then I'll show you. We're going to go to Desmos. And if I want the t-distribution, then instead of normal distribution, you're going to click Functions and scroll down to t-distribution right here. So you select the t-distribution. And then you have to type in your degrees of freedom, let's say 1 degree of freedom. And then the CDF is still left area, but the quantile function is still left bounds. So it works the same as the normal distribution, but just...
Do you ever need, I thought there was just one distribution for t-distribution.
So the t-distribution is a little bit silly because it has different degrees of freedom. As long as you pick a real number greater than 1. There's actually a lot of different t-distributions. Do you see how the blue curve just changes just a little bit when I change the number of degrees of freedom? So
When would you need a CDF for t-distribution? I thought like in our questions we only used was the t-distribution.
okay, a good question. When we are dealing with fractions, fractions follow the standard normal distribution.
Is that CDF or
Both.
how do you know which one to use?
If it's a confidence interval, you're going to be using the quantile function. If it's a hypothesis test, you use the CDF. And then for means, we use the t distribution.
So hypothesis is which one again? CDF.
Mm-hmm.
And then intervals are quantile function.
Okay, does that clear it up a little bit? Okay. Well, in any case, back to our example. This is a case where I am constructing a confidence interval. And so just to make you even more confused there, Nora, I'm constructing a confidence interval about a mean, but I'm still using the standard normal distribution because I don't know my sample size. The question is asking me, what does my sample size need to be? Okay. And since I don't know my sample size, I don't know what the degrees of freedom would be for my t-distribution. And so to play it safe, the most conservative choice of distribution would be the normal distribution. Again, I can't use the t-distribution here because I don't know the sample size. T-distribution needs degrees of freedom. Degrees of freedom needs sample size. Sample size is what we're actually trying to solve for here. So I cannot use the t-distribution, so I'm going to have to use the standard normal anyways, even though this is a confidence interval about a mean. In a previous question that we did maybe, I don't know, Friday. In a previous question, we were constructing a confidence interval. And when we constructed this confidence interval, we did know the sample size, so we did use the t-distribution when we constructed a confidence interval about a mean.
When do you use the z one? Is it whenever you don't know the standard deviation?
The z is going to be whenever we are dealing with fractions, because we assume that if n times p times 1 minus p is greater than 10, that the sample fraction is approximately normally distributed, so then we can use the standard normal distribution. That's when we use the z-score. Z-score is our standard normal distributed.
I thought in 5 you were going between, you had to choose if you could use the T1 or the Z1. There's like some rule about, okay, if the population fraction is known, then...
It's not the,
Or the rule-
it's about whether or not you know the standard deviation, right? If you actually somehow had knowledge of the population standard deviation, it would be a z-score. If you don't have knowledge of the population standard deviation, you're just approximating it with a sample standard deviation, then you use a t-score. So whenever we are calculating sample means, we don't know the standard deviation for the population. We can only approximate that with the sample standard deviation. And so in that case, we have to use the t-distribution because we don't actually know the standard deviation exactly. In this case, with these kinds of hypothesis tests, we actually do know what the population standard deviation would be if we assume that the null hypothesis is true. Because our null hypothesis in these cases is saying that, like, my population fraction is equal to some number. And if we assume that's true, then the population standard deviation of the sample fraction is the square root of p times 1 minus p divided by n. And so this is known, but only in the case where we're dealing with the fractions. In the cases where we're dealing with the means, we do not know the population standard deviation. So we use a t. Okay, all great questions. Let's finish up this example that we're doing here. We were just in the middle of using the standard normal quantile function in Desmos to get the answer for 0.975. And when I plugged in 0.975, I got out the answer 1.96. So my sample size is going to be 1.96 times 6, because that's in my problem statement, divided by 2, because the margin of error is in my problem statement, and then square it. So then you can get out your Desmos, or you can get out your calculator and just type in 1.96 times 6 divided by 2, and then take that number and square it. And I get 34.57, but we are going to round up, and we get 36. Because we don't want a fraction of it. No, 35, sorry. I can round. 34 rounded up is 35. Because we don't want a fraction of a person in our experiment. We only want entire persons participating. So I need to survey at least 35 people.